Just as a Formula One driver pushes their car to the limit, AI workloads are pushing the limits of scale and speed. But debris on the track can cause a crash even for the best champions. And just like that, network cards and links flap and cause crashes for AI workloads, even for the best engineers in this room, which is all of you. I'm Lerna Ekmekcioglu. I'm a solutions engineer at Clockwork, and we provide solutions for network performance acceleration and resilience for traditional workloads and AI workloads. Prior to this, I was at AWS for 3 years as a solutions architect, and before that, I was in large financial services companies. There I enjoyed working on problems of scale like centralized authentication systems, distributed caching for an investment management portal, low latency monitoring for all servers in the firm, and the downtime of any one of these systems meant a 3 a.m. page, in the middle of the night, and I like sleep just as much as every one of you here. So we needed solutions that are highly available, scalable, and resilient. For AI workloads, similarly today, we have challenges in the networking space that I'll cover along with demos, and I'll touch upon learnings of a solution that provides resilience against link and network card flaps so that our AI workloads can run at full speed, just like a Formula One champion's car. So that was my background. How many folks here, I'm curious about you, are on the application side and AI/ML space or HPC space, engineers, researchers, data scientists, anyone? I see one hand raised. Okay, how many folks, wait, two. How many folks are in the application space, not on the infra? Not, okay, a couple of hands raised. There's going to be lots of you, obviously, on the SRE Infra Eng platform, but how about AI/ML, HPC, GPU clusters? A couple of hands raised. Very cool. Well, I hope that there's something for every one of you today. This is Flappy. I'm going to be using Flappy to indicate piece of useful information throughout the talk. And these are the challenges that I'm going to eventually get to, but first, I'm going to cover just a little bit of background so we're all on the same page. So first up is AI workload layers. So this is how we're building our workloads. On top, you have the workload itself. Maybe this is an LLM model. You're building it using libraries and frameworks for optimization and deep learning, maybe like DeepSpeed and PyTorch. If you have large-scale jobs, then you need inter-GPU communication, and for that, you're using things like collective communication libraries. That's NCCL for NVIDIA GPUs, RICL for AMD GPUs, for example. And at the bottom, the network device that needs to be RDMA capable, that is speaking over fabrics like InfiniBand or RoCE v2 typically. Now, RDMA is a key feature. It enables fast data transfers, and you can go from one node to a remote node's memory over the fabric, over the network, bypassing the kernel. And the fabrics that we're using for this is providing high throughput and low latency. These are things like InfiniBand, which is, we see this a lot in the field. I would say majority of what we see in the field happens to be InfiniBand. And InfiniBand relies on proprietary protocols and proprietary hardware, so you need proprietary network cards and switches and cables, so it can get costly, but it performs really well. That's why we see a lot of this in the field, I think. And RoCE v2, which is RDMA over Converged Ethernet, it relies on standard protocols like UDP, IP, and Ethernet that we all love, and standard hardware, so it is not as costly, and it performs comparably well. We do see RoCE v2 in the field, so it's not like there's no RoCE v2 clusters there, but more InfiniBand. And Ultra Ethernet is what's coming up. This is actually the more performant kind of Ethernet transport protocol that is being baked. It's an improved transport that provides better congestion control, and ultraethernet.org has really nice kind of information about this in more detail, but this is what's coming up in the future so that we can still utilize our standard protocols and standard hardware, but get better performance for our AI and HPC workloads. Now, if you look at the networks in which we run these GPU clusters, they actually are divided into two sides. There's front-end networks and back-end networks. Any Star Trek fans in the room? I am hoping a couple. Okay, great. So front-end network is like a bridge on a ship. It doesn't have to be a starship. It can just be a regular ship, like captain's quarters. And the back-end networks are like the engine room. So here I have 4 nodes in a GPU mini cluster. And I have front-end network cards that are speaking over Ethernet. Maybe you have your storage or compute nodes attached to this. So you can think of this as your north-south network. This is the front-end network. And in the same 4 nodes, you also have the back-end network cards that are speaking InfiniBand or RoCE v2. And this is the back-end network. And what do I mean by each one of these? So in the front-end network, what you're doing is typically you're ingesting data, maybe for your distributed training, you're doing some logging, monitoring, you may be storing the model state, so you're doing some checkpointing into the storage systems. And in the back-end network, what you're doing is you have these network cards, maybe they're forming a ring, and you're doing this distributed training and distributed inference, so the heavy lifting of training and inference is happening in this backend network that is speaking InfiniBand and RoCE v2. So I really want to focus in there because this is where some of the challenges are happening. There are challenges in the front-end networks as well, but my talk is going to be more geared towards the backend networks. So it's really that pink layer of the cake, which is the collective communications layer where you have GPU to GPU communication. So here I have 2 nodes, and each of the nodes have 8 GPUs. Those are the orange boxes. And I have each GPU connected to a dual-ported network card, so the blue boxes or rectangles. GPUs are generating messages. Messages are split into chunks. Chunks are assigned to queue pairs, and queue pairs we can think of as sockets. And the network card is taking all of this, packetizing it over the fabric, InfiniBand or RoCE v2, and sending it to the receiving network card, which is passing it up the stack. Next, I want to look at the demands of these workloads from their networks. But for that, I want to take a step back, because I think a lot of us are really familiar with traditional networks, which to me are like busy streets in a big city, like New York City, where, yeah, we have the subway system, they're great, but maybe the buses are not so great. And AI networks are like a high-speed racetrack. So in traditional networks, you actually get a lot of delays and packet drops. So you really do expect best effort service, and that's what you get. AI networks, on the other hand, they are built for lossless transmissions, so you get minimal delays and best performance. Traditional networks, network cards operate typically at 25 gigabits per second. Maybe it goes all the way up to 100 gigabits per second, but not more than that. And you really have an understanding of a safe link utilization rate. You do not want to clog the pipes beyond 50%, or else you get more packet drops, more delays, more congestion, angry customers. AI networks can go anywhere up to 800 gigabits per second for the network card speeds. And you have fewer flows, but they're highly utilized in terms of bandwidth. So you have like 95% or more link utilization. If you then look at an LLM training run and profile it, you'll see that it actually consists of phases of computation followed by communication for each and every iteration. And 30% or more of the overall job completion time is actually spent when GPUs talk to each other. So it's spent on networking. So if you look at an all-reduced collective operation, I have here 4 nodes, and components of the sum, they're getting passed around the ring. And then the sum is computed. And then it gets passed around the ring once more time so that each and every node has the total sum. So the finish time of the operation is actually based on the sum of the latencies in the ring. Just like at a pit crew, the crew is not done until the slowest team member is done. GPUs, they're not going to proceed to their next step until all synchronize their partial result, like partial gradients, so that they all have total gradients. So slowest team member is actually determining the speed of the team. And just like that, slowest flows or nodes are determining not only the job completion time, but also throughput for the job. And I'll show this in a demo. So what are those challenges that we see in the field? You know, we talk to enterprises, we talk to neoclouds. These are the challenges that we see in the field for AI workloads in their networks. Lack of visibility, which is not as appreciated. Lack of reliability, which is paging people, so it is more appreciated, I think. So first off, lack of visibility. So here's an issue that a team faced. 6 months prior, they had a top-of-rack switch, and it had down uplinks. And they only realized that 6 months later. And they didn't know why these links went down in the first place. 6 months had passed since then. So we believe that this is happening because teams are lacking real-time insights into connectivity between the nodes in the GPU cluster, into the quality of the paths. They only get aggregate level metrics, maybe at network card or switch counter level, but they don't get fine-grained metrics down to the queue pair level. So they're unable to identify and resolve root cause of issues quickly when it comes to connectivity, not only at the GPU cluster build time, onboarding time, UAT testing, those GPU clusters, before handing it over to the application owner, but also for the AI workloads at runtime. So this is our foundational research. It is software-based probe mesh clock synchronization. It's high precision at scale, and it is measuring one-way delays accurately. And it's my first demo. I don't know how many people are in love with networking, but it takes just a couple of minutes, so we'll go through it and we will build on the upcoming demos based on the information from this, so bear with me. So here I have 4 nodes. 2 of these nodes are in one rack, and 2 of these nodes are in an adjacent rack. Each of these nodes, they have 8 GPUs and 8 dual-ported network cards. So each of these squares, they're actually a network card. Right now, they're showing as green because the probe delays in this probe mesh are less than 5 microseconds for this cluster. That is a healthy state. So if I look at one-way delays in between these 2 network cards, in between these 2 nodes that are in the same rack, it will be below 1 microsecond. And here I'm getting 870 nanosecond one-way delays per queue pair, and I have 4 queue pairs in between these 2 network cards. If I look at the same one-way delays across these 2 nodes that are across racks, I'm getting 3.24 microsecond per flow. And right now I don't have any workloads running, so the one-way delays per queue pair are looking about the same. What I'm going to do next is I am going to kick off a workload just to see how that changes the delays. So here I'm kicking off an all-reduced job, just a simple standard all-reduced job, and it's in between nodes 4 and 6, so I should be able to see the throughput of these 2 nodes go up. And I'm using 100 gigabits per second network cards here. So I have an understanding of what is a good throughput I should get out of these nodes, and right now I'm not getting that. So I'm getting only 1.38 terabits per second, and we'll look at why that is at the end. And just to be kind of very explicit about what's happening at the network card level, I'm only getting 86 gigabits per second. 100 is my line rate, so it's not close enough to that line rate. I should get a bit more than this. If I look at one-way delays, just one more time, before running the workload versus after running the workload and how it changes. So before, without the workload, 3 microsecond per queue pair. And after running the workload, I'm getting a bit more as expected since I have those data packets. So I have 4 microsecond per queue pair one-way delays. And next, I want to look at those slow edges. So some of these red lines, they are indicating slow edges. And you can see at least one queue pair actually has a one-way delay of 50 microseconds versus the other 3 were at around 2.6 microsecond range. So one of the queue pairs is much slower than the rest. So I have really slow queue pairs here. And if I pick on each and every one of those red edges that are slow, I'll see a similar story. So here I have one that is at 7 microseconds versus the other 3 are at like half that in terms of one-way delays. And I'll pick on one more. So this last one, it's around 46 microseconds versus the other 3 are at 3 microsecond range. And we will actually look at this later in another demo as well. This next issue is actually very close to the heart of everyone because they're getting paged for this issue. There's angry customers. So in this case, the links flapped over 10 times within the past hour, and this team had to send technicians to the data center to swap out cables. Just curious, how many people here following semi-analysis, which is like an AIML publication. I see a couple of hands raised. It's a well-respected AIML publication. It's good to follow. And according to semi-analysis, this is a common problem in large enough clusters where you have thousands of GPUs, and accordingly, you have thousands of links and thousands of optical transceivers. So even if a single mean time to failure per link is 3 to 5 years per optical transceiver, because you have so many of them, you may see a job failure as early as within the first half hour of that job running. And this is happening because those optical transceivers, they tend to overheat or dust particles are getting in the way. So the link flaps. And what do I mean by the link flapping? So the network link temporarily drops, goes from up to down. This can last in order of seconds. If it's a few seconds, it may self-heal and recover if it's below, say, Infiniband timeout limits. But if it's more than a few seconds, then collective communication typically times out and the job fails. And when it happens, when the job fails, you may have to fall back to a previous checkpoint if you took one. And in the field, what we see is at best, people are checkpointing every 30 minutes because checkpointing is also expensive. So you're losing the time since your last checkpoint till the time that link flapped. In addition to that, also you're losing the time that you took to recover from the issue. And you're losing the efficiency out of this GPU cluster. So if your cluster had a personality, which one would it be? Would it be the ghoster? It drops connections without warning. Or would it be the Zen master? It's always stable. So any ghosters in the room? No ghosters. Everybody's cluster is a Zen master? All right, whoa. Okay, I want to talk to you. All right, so in the field, what we're seeing is that there is these ghoster clusters, and people are trying to get to Zen master. So for the next demo, we are going to be simulating a link flap. And for that, you can think of these technicians going into the data center and meaning to maybe install a cable and then unseating unintentionally one by mistake. And this happens because you can see the back of that cluster, 100,000 links or cables. And that is going to be our link flap. And then we're going to recover from it by reseating it. So first, I'm going to start from my baseline. So I'll kick off a job, an all-reduced job again, in the same cluster that I was before. This is a cluster in the cloud, in Oracle Cloud. So first, I should see the throughput for these two nodes go up. And it's 100 gigabits per second links. And right now, I'm getting actually the best throughput I can get in this cluster, which is 1.47 terabits per second. And we're simulating a link flap. So let's say by mistake, we knocked off one of those cables. So the NIC1 is the one that I flapped. So that just went down. At the same time as that went down, the job crashed. So this is a typical issue that happens. And when it happens, then we have to fall back to a previous checkpoint if we took one. So just to show you what happens if we were to recover that link so that it's back, so NIC1 will be green again. Now it's just up again, and the job doesn't come back, so the job remains dead. So this is the actual issue. Now you have to fall back to a previous checkpoint, load all the training data, all the weights into the GPUs again, and start over. And just to show you that I didn't just play with the colors there, I'm not lying. I know this link is healthy because the probe traffic is back. And I can see the duration for which it was down when it flapped. So the link is truly back, but the workload didn't come back. So here I have 3 runs. This is in a similar cluster. So the first run is the no failure. So the baseline, 1.37 terabits per second, is the Zen master. The second run is actually the ghoster in this case. The NIC flaps, the job dies, the NIC revives, the job stays dead. So this is the actual issue of what happens in GPU clusters today. The third one is of a solution that auto-recovers from NIC flapping. So the NIC fails, the job continues, but you can see slightly degraded throughput. The reason for that is you lost one NIC, but the remaining NICs are doing double duty. So you lose a little bit of your throughput, but when the NIC revives, then all the NICs are doing normal duty, so you actually gain back to your original throughput. So the learnings from this solution is that you get a choice of when and if to fix this flapped NIC. And one idea can be to run until the next checkpoint, at which point you can recover the flapped NIC, revive it, and that way you're eliminating downtime. My last demo is about contention. And the contention, I'm going to first start at one job, all reduced job. I would say this is not something that we see so much in InfiniBand clusters, because in InfiniBand you have adaptive routing, but you may see this in RoCE clusters. And I think Ultra Ethernet may actually bring some solutions to this as well. So the first, let's see the healthy state. Again, we're getting 1.47 terabits per second with one job running. I'm going to kick off a second job to create some contention in this cluster. Second job is an all-to-all job. And these are two cross-rack jobs, so they're going to contend that the spine layer flows. Previously, I was getting 92 gigabits per second per network card. It's the 100 gigabits per second cards. But because I kicked off the second workload, because of the contention that got started at the spine layer, so the throughput for both jobs actually got reduced. The first one is only getting 860, second one 495 gigabits per second. The network cards are only able to do 50 and 30 gigabits per second. So I basically am down to 50% or less. And the reason for this has to do with the one-way delays per queue pair. These are going anywhere from 3.4 microsecond for the fastest one to the slowest one at 50 microsecond range. So I have a ginormous distribution for the one-way delays per queue pair. I have really, really slow flows, slow queue pairs. And the network is also telling me with explicit congestion notification marks that it is congested. Remember, those slowest team members slowing down the speed, slowest flows are slowing down the throughput of the job. So here I have 3 runs again. The first run is just an all-to-all job, 100 gigabits per second line rate. I'm only getting 84 gig. The reason for it is in the graph below. Queue pairs with high one-way delays, some of them are at 50 microsecond range, a lot of them are in the few microsecond range. If you introduce another all-to-all job, here I have 44, 39 gigabits per second for each, so 50% or less throughput is what I'm getting because of that contention over the wire at the spine layer. So one-way delays actually, for some of these flows, shot up to 100, 150 microsecond range. And the last one is of a solution that is minimizing those one-way delays so they converged. And maybe they converge to, say, 30 microsecond. So everyone is running at the same speed. You don't have these very, very slow flows. And that is enabling the throughput for both of these jobs to reach closer to line rate at 92 gigabits per second. If you could wave a magic wand and get rid of a networking pain forever, which one would you choose? No more link flaps or self-healing NICs? No more link flaps. Okay, maybe 1 or 2 or 3, 4. Going once, going twice, okay. Cool, 5. Self-healing NICs. Oh, you're for the self-healing. Okay, everyone wants to self-heal. Okay, come and grab your magic wands after the talk. I have them. Okay. So lack of visibility down to the queue pair level is actually slows down diagnosis of connectivity issues and also resolution of those issues, not only when we're building those GPU clusters, but all the way to AI workloads runtime. We don't appreciate this yet, but I think we will eventually. NICs and links flap, and that's because overheated optical transceivers or dust particles or other reasons, and these can cause jobs to crash, so we have to check points according to our business requirements so that we can recover from them gracefully. And finally, delays in our slowest flows can degrade our throughput by as much as 50%. And my last bit of information is paying homage to Lucille Ball, without whom we would not have Star Trek. We are hiring in this region, so come and talk to me, and thank you for your time.